Today, on how it's made. Sails. Walnuts. Wheel immobilizers. And honeycomb structural panels. A sail is essentially a vertical wing that provides forward thrust and lift to propel a boat over water. It's impossible to know who came up with the concept because boats with sails have been plying waterways for thousands of years. But when it comes to their design and construction, today's sails have come a long way. For thousands of years, sails were square. But in the 3rd century, triangular sails appeared on the Mediterranean. The shape enabled boats to sail into the wind as well as with it. Modern racing sails are made of laminated synthetics. They start with a plastic membrane. Rollers apply a hot liquid adhesive to one side in measured amounts because even a couple of extra grams would weigh down the sail. They press a scrim onto the hot adhesive. It's a super-strength synthetic called aramid, which will keep the sail from tearing. Then it's over to a computerized laser that cuts patterns out of the scrim-reinforced plastic. A worker rolls up each panel to transport it to the next work table. Here, they tape 10 to 20 of the panels together using heavy-duty PET plastic with an acrylic adhesive. Now hundreds of small jacks stretched aluminized plastic around a framework, pulling material into a curved aerodynamic shape. This mold will be used to shape the sail. The team stretches clear plastic film over it. Then they drape the joined panels over top. They use ropes and clamps to pull it to the contours of the mold. And now, they're ready for some super tough synthetics, aramid and carbon fiber yarns. The yarns have been coated with adhesive so they'll stick to the plastic film. A robot rolls the yarns onto the film while a worker follows in a harness overhead to keep an eye on the job. The robot applies the yarns in a pattern plotted by an engineer to anticipate the wind load on this sail. The robot now switches from a vertical path to a horizontal one, applying yarns in a transverse pattern. The team installs a long, narrow pocket over that section. A batten will later be inserted in this pocket to control the sail's shape. They pull another layer of scrim-enhanced plastic on top, and now all the layers of the sailcloth are in place. A worker hovers overhead to inspect the surface for defects. They now seal the assembled sail in a vacuum bag and attach hoses. The hoses suck out the air, pressing the layers of the sail together. Now the robot applies heat to the sail. It activates the adhesives in the plastics to laminate the layers together, and it also sets the three-dimensional shape of the sail. A worker inspects the job with a magnifying glass. Then it's over to a revolving sewing turret. As the sewing machine turns, it pulls the sail forward, allowing the operator to stitch hems, grommets, and reinforcements onto it. They apply the corporate logo. Next, a worker walks the length of this enormous sail to inspect it. No imperfections will be tolerated. After all, this is a big-ticket item. Large racing sales can retail for hundreds of thousands of dollars. Sophisticated engineering and high-tech materials have produced a racing sail that's lightweight yet incredibly strong. There may be rough water ahead, but with technology on their side, this crew should be able to sail right through it. The walnut has been cultivated for thousands of years, but its actual discovery remains a mystery. Some of the earliest evidence of the walnut comes from the region of Persia in 7th century BC. Back then, royalty had dibs on this nut, and commoners were forbidden to eat it. Thankfully, that's ancient history. Today, the walnut is mass-produced to meet a global demand. It starts in an orchard like this one in California. Walnuts take 5 years to grow, and they emerge shrouded in protective husks. Using mechanical shakers and sweepers, workers harvest the walnuts. Once the husks have been peeled off, it's over to the receiving pit at the processing plant. This machine separates out any rocks or sticks, then drops the walnuts into a conveyor. At the end of the line, the nuts spiral off and land softly in cooling bays below. There are 8 bays that hold over 1,300 tons of walnuts. The walnuts are funneled into these sealed chambers for fumigation to eliminate insects. After 28 hours, they're on the move once again. They fall between rollers. The gaps between these rollers are tapered to allow the small, medium, and large nuts to fall into separate lanes. This sorting system will allow them to be cracked by machines geared to specific nut sizes. These large walnuts head up a conveyor called the cracker belt. At the top, they enter the cracker. It's a revolving machine with pistons, one for each walnut. The technician activates the pistons to press against the nuts. The pistons apply a precise amount of pressure to crack the shells without damaging the nuts inside. The nut cracking has been slowed for our camera, but in reality, this is a high-speed operation. The nuts, shells and all, fall onto a conveyor. The pistons have cracked between 80 and 90% of the walnuts. To capture the rest, the whole pile shakes its way towards a second group of sizing rollers. The smaller pieces drop through the gaps and go for further processing. The larger ones continue on to a machine called a recracker. There, the nuts travel through slats in a revolving cylinder. Inside those slats are little knives that break up the whole nuts. After some of the larger shells have been removed, it's onto a giant sifter. The nuts and shells bounce on a shaking screen. The smaller bits fall through, and the larger ones remain on top. The holes in the screen become progressively larger to sort the pieces into 8 sizes, which differ by a fraction of a centimeter. The bigger, choicest walnuts fall into a separate chute. The smaller pieces will be used in baking, among other things. A high-speed belt sends nuts and shells flying through the air to allow a computerized camera to detect shell fragments and activate a system to blast them off the production line, leaving that prized kernel, the walnut half. An inspector removes any remaining shells or unacceptable nuts. Then, the walnuts enter a vacuum chamber, which suctions away any last crumbs. They exit on a spiraling slide and land in a box. This packer portions out bulk product for the food industry. He removes nuts from the box until it reaches the correct weight. These walnuts are on their way to adding crunch and flavor to cookies, cakes, and other good stuff. The walnuts in this box have taken years to grow and a couple hours to process, but in the end, the wait is more than worth it. On the street, it's known as the boot. Accumulate a few unpaid parking tickets, and you may very well find your car wearing one. Municipalities use wheel immobilizers to clamp down on offenders, while universities use them to deter illegal parking on campus. The boot's dome goes over the rim. On the other side, its inner arm hooks in between the rim and brake. A secure bolt clamps those outer and inner parts together, immobilizing the wheel. Boots must be strong and tamper-proof, so the main components are made of steel. This steel tube will become the boot's outer arm. This steel bar will become the stand that props up the boot during installation. This flat steel bar will become the inner arm that hooks between the rim and brake. They bend it lengthwise to give it strength. Then they bend it into the final shape. Now back to the tube they cut for the outer arm. After bending it in 2 spots, they drill 2 holes for the tube that'll house the secure bolt. They bend a flat steel bar to make a stiffener that reinforces the inner arm. Meanwhile, that steel bar they cut to make the stand goes onto a machine called a rod bender. A welder now fuses the tube to the outer arm, then welds that assembly to a part called the body box. After welding the stiffener to the inner arm, he welds a pin through holes in both the arm and the other end of the body box. So now the inner arm hinges on the box. After a coat of baked-on enamel, the boot's body is complete. The dome measures 30 centimeters in diameter. First, they weld a bracket to it. Next, they fit a sleeve into the bracket and thread a pin through them both. Then they weld the pin to the bracket. So now the sleeve pivots. This, too, receives a baked-on coat of enamel. Now they glue a rubber trim over the dome's edge so that booting a car doesn't damage the rim. It's time to assemble all the parts. First, the mechanism that clamps the boot's inner and outer arms around the tire. Using a special key, they screw it into a stainless steel nut inside the bolt tube. This spring holds the inner arm in the correct position. The stand goes on with a bolt. The stand elevates the boot off the ground, enabling the installer to turn the secure bolt key. In this cutaway, you can see how turning the key moves the secure bolt forward, pushing the inner and outer arms together to clamp the tire. Next, they slide the dome sleeve over the body's outer arm. They align the hole in the sleeve with a hole in the arm, then bolt the parts together. The arm has several holes, so the boot can accommodate wheels of different sizes. Every boot gets a metal plate bearing the model and serial number. The boot manufacturer records who owns the boot and won't issue a new secure bolt key without proper identification. From the mechanics to the cabin, aircraft are made with the most lightweight, high-strength materials, such as honeycomb structural panels. These make up the support structure hidden beneath the flooring and behind the walls of, among other areas, the lavatories, galleys, and stow bins. The cells at the center of the structural panel are hexagonal in those designed to lie flat, and rectangular in curved panels. Producing the core begins with giant printing cylinders. Etched into their surface is a pattern of lines. They rotate in heat-activated adhesive, printing the line pattern onto paper that passes between them. This paper is made of thermoplastic, but depending on the type of panel, it can be another kind of paper or even aluminum foil. This machine cuts the paper into sheets, anywhere from 500 to 2,000 sheets, depending on how thick the cores will be. The machine then stacks the sheets in a specific sequence. Every other sheet is offset by half a line. This back and forth pattern is what forms the core's honeycomb cells. The stack now goes into a heated press, which activates and cures the lines of adhesive, bonding the sheets. After an hour, they remove the stack and attach aluminum foil loops along its perimeter. Then they stand the stack on its side and hook those loops onto the steel pins of a device called an expansion frame. It slowly pulls apart the sheets, opening the honeycomb cells that the special stacking sequence formed. To ease the expansion process, they soften the paper with water. This is a time-lapse shot. The full expansion takes about 15 minutes. Next, the block goes into an oven, where it bakes for about half an hour at 275 degrees Celsius. That heat sets the thermoplastic paper, locking in the honeycomb shapes. Now, they repeatedly submerge the block in a vat of resin, baking it after each dip. Here, an aspirator sucks out the excess resin. Then, after a final baking, an automated saw slices the block horizontally into several cores. Then it's over to the assembly table. They construct a structural panel like a sandwich. The honeycomb core in the center, this one's made of aluminum foil. Then on either side are the panel's outer sheets, in this case made of carbon fiber. On the top and bottom, workers position a sheet of release paper to prevent the panel from sticking to the metal sheets that hold everything in position for now. Workers load the assembly into a press. The heat and pressure combined bond all the layers. About an hour later, they take the sandwich out of the press and remove the metal sheets. Workers slap on labels identifying the product and manufacturer. Then they shear off the panel's rough edges. The factory subjects some samples to a series of quality control checks. This load test, for example, assesses how much the panel can flex and how much weight it can withstand before snapping. Whatever the materials, thickness, or density, these structural panels all deliver maximum strength with minimal weight.